theme of going beyond things in this workshop. He's going to take us beyond software.
That's right, yes. When I saw the title of the workshop, I kind of pondered what I can contribute to it, and I was kind of stumped because 100% of what I do is like differential privacy, or like we're barely trying to kind of achieve differential privacy, or trying very hard. So like going beyond differential privacy is like beyond my wildest dreams. So I decided to kind of take you beyond in a different direction. Basically, this is like the picture that we all know and love, and there are some salient features of this picture that we sort of like we've gotten used to, but apparently they still rub certain people the wrong way. And here I want to put up a quote from the paper by one of the prominent cryptographers, Phil Rogaway, from his essay titled "The Moral Character of Cryptographic Work" from a few years ago. And in that paper, it's a kind of long essay on kind of musings on kind of this sorry state of modern cryptography. But one quote is particularly relevant as it relates to differential privacy. It says that the model of differential privacy implicitly paints the database owner, the curator, as the good guy, and the user squaring it, the adversary. If power, meaning the man, would just agree to fudge with the answers in the right way, it would be fine for it to hold massive amounts of personal data about each of us. But the history of data privacy breaches suggests that the principal threat to us is from the database owner itself, and those that gain wholesale access to the data. I saw he reached out to me with an early draft of that essay. I kind of addressed some of his points. He summarized my point of view fairly. It's in the paper. It concludes with saying that the definition of differential privacy is agnostic to the data model, which I tend to believe in. But then he gets the last word, which is no actual mechanism can be agnostic to what data resides where. And at the point when a data mining architecture mechanism is laid down, considerations of efficiency, familiarity, and economic make it easy to predict what will happen. Almost always, a centralized design will emerge. Which leads him to the very damning conclusion that, to me, differential privacy may be as authoritarian in its conceptual underpinnings as identity-based encryption. So basically, it's like Mein Kampf, IB, and like differential privacy kind of. So one of the examples that I've given him that kind of goes against his thesis is that local differential privacy explicitly gives power to the end users. Yes, like it's perfectly compatible with the definition, with the canonical definition of differential privacy, and it achieves the very ends that he kind of argues for. The problem with local differential privacy, and like I put up this, like I used this slide at the boot camp at the very beginning of the semester, that it's a privilege of the rich. It's no small accident that the companies that publicly deployed local differential privacy are companies with like more than 1 billion users. It's this 3 comma club. And again, that kind of would. If I kind of can continue my imaginary conversation with Phil Rogaway, he'll say, "Ha, I got you there. Like it's only the companies with the $1 trillion valuations can afford to do local differential privacy, and like okay." So he would say something nasty about kind of capitalism. Okay, the second argument that I kind of put forward, which is that there is an alternative to implementing curator, as this mechanism that hoards data and kind of mediates access to data. The alternative is to simulate a curator via a multi-party computation. Yeah. And for those of you who are non-cryptographers, that's a technology that emerged in the early 80s that allows a coalition of people, mutually distrustful individuals, and like the distrust goes both to argue security, like it's we have to design our mechanism as to be resistant to some participants who work to undermine the working of this mechanism, but it also kind of allows some measure of privacy. If not all participants collaborate, then typically we can have a very good protection for data that we contribute to the mechanism. And not coincidentally, one of the very early papers on differential privacy that appeared in 2006 explored this very model. So specifically in that paper, we consider the question of the sort of the canonical problem in distributed computations of computing the sum of individual bits. And computing the sum in an MPC way is very simple. The hard part turns out to be not impossible, but like the more interesting, mathematically interesting part ends up being generating noise in an efficient manner, it's not surprising that generating the Gaussian noise, the Gaussian noise is a better match for this distributed generation, and that paper is best known for introducing the notion of epsilon delta differential privacy and for introducing Gaussian noise in the differential private context. To be fair, the differential privacy, Gaussian noise as a way of protecting privacy goes back to the vertically partitioned databases by Kobe and Cynthia. But what it? That's right. Yeah, even earlier than that. Yes. So, kind of that concept of replacing the curator with a coalition of people working to implementing multi-party computation was very much on our minds at the very beginning of differential privacy. Fast forward 13 years, and I've taken this snapshot from a Google I/O, which is the main Google developer conference, from the keynote address by Google CEO Sundar Pichai, where he presented yesterday, exactly 24 hours ago. He talked about the work on federated learning that currently powers Gboard, at least for American English, where your devices engage in exactly the kind of multi-party computation that kind of we sketched out many years ago. To be precise, currently these devices don't generate noise distributively. So what they do is that they kind of the aggregator updates to the Gboard model. Gboard is like what kind of I think specifically it's this one line where it proposes suggested words.
Yeah. Do you have to clarify in what sense it's exactly the same multi-party computation?
It aggregates, think of it's this part.
It does aggregation, but doesn't.
It doesn't.
It doesn't do any kind of.
Yeah.
It's not differentially private.
It's this part.
It's not differentially private, and it's not kind of secure in the same way as multi.
Not in the same way, but multi-party computation is a very. It's an umbrella definition. It can tolerate many possible.
So for those of us who've heard various, can you say precisely what it is? Is it honest but curious aggregation?
It's so I should have known an answer, but kind of there's a paper from 2017 that on the bit curious, resistant to the kind of N over 3 coalition of corrupt parties. I cannot say whether it's exactly the same model which is implemented in the current iteration of Gboard. I just don't know this information.
You don't know.
I don't know what is currently running on your cell phones, on your Android phones, but there's a well-documented protocol that is a close approximation to what is being run. Okay, so this is from the point of view of multi-party computations. That's really a baby step of computing this distributed sum. What about doing more complex computations? And a canonical problem in multi-party computations is called shuffling. It's called a permutation. And again, we kind of saw potential for using this multi-party capability to enhance our differential privacy guarantees. We first described it in the Proclo paper that appeared at the Systems Conference in 2017, and basically at the heart of that proposal was the idea that we'll do some local differential privacy on the devices, then we'll pass this inputs through a sequence of shufflers, and the output is going to be a fully anonymized version of what came in. And again, that model is being implemented in this new operating system that Google is working on. It's called Fuchsia, and there's the system is fully open source, and you can check out the progress on implementation of this particular technology called Cobalt under Fuchsia. And it's based on the kind of this paradigm outlined 2 years ago. This shuffle model was led to fairly interesting and insightful work in theory that demonstrated that it is fundamentally sound approach to amplifying local differential privacy, of translating local differential privacy guarantees to a stronger central differential privacy. But again, cryptographers in the audience would recognize the shuffle model as something that appeared in the cryptographic literature back in 1981, and that was a canonical problem for kind of anonymized communications, or a canonical building block for anonymized communications, where exactly this architecture was described by David Chaum. And this slide has appeared in hundreds or thousands of talks, and usually, like as a motivation, and usually it was introduced as a way of conducting elections. And the way this slide was motivated is by saying that let's imagine that these boxes are going to be run by this mutually distrustful parties, EFF, ACLU, the Republican Party, the Democrat Party. And as a card-carrying cryptographer, which is actually true, I'm a member of ICR, I'm kind of I have to take it as an article of faith that that slide makes sense, because, like, again, it's been used in thousands of papers. But let's face it, even though this idea was articulated back in 1981, it's now been done. Why is that? Well, because like EFF and ACLU, they don't run services. It's not their thing. The Democratic Party and GOP, they do, but they wish they hadn't. And even though like they are mutually distrustful, we know that both of these parties can be compromised by a single agent. who kind of coordinate their secrets and kind of will mess up with their internal operations. Yep. So really, I'm sad to say it, but that particular slide is a science fiction. And all implementations of multi-party computations, they didn't follow this paradigm. The parties which were running the servers were basically paid for and operated by someone who had a stake in the final outcome. So if we acknowledge this truth, what are the reasonable ways of bringing this closer to reality? So again, I want to emphasize that we like the idea of running the shufflers. We have theoretical evidence that they amplify privacy. Not only the evidence is there, but also kind of the intuition is there. If the inputs are fully stripped of identified information and like put in a large bag, then the output is going to be more private than before. And again, I don't have to appeal to theorems. This is how elections have been conducted for centuries. It's called the Australian ballot, like the secret ballots, using these hardware devices called urns. And to kind of get us closer to implementation of this vision, I want to bring up what's called as SGX, software guard extensions, that were introduced by Intel a few years ago and kind of are commercially available starting 2015. And basically, they enable creation of secure enclaves. And the secure enclave, I won't get into kind of the technical definition of what it is, but basically it's a code that can be executed in a completely opaque manner by the host operating system. So the operating system controls the inputs, observes the outputs. It doesn't control what's going on inside this black box. And this black box can do encryption, can do decryption using keys that are not accessible by the host operating system. It supports remote attestation, supports sealing. I'll say a few words what remote attestation is. That's kind of a relatively complex picture, and the actual protocol is a bit more complex than this diagram makes you believe. But in principle, what it says is that the challenger, which is a party that is trying to that relies on enclaves for execution of its code, it will verify that the code running in a data center is what it think it is, what it claims to be. Like it can authenticate the code exactly. And there's it can enable keys that are only accessible within this black box. So it will kind of enable. It can negotiate keys, either the private keys or public private key pairs that are only accessible to within this black box. And the beauty of it is that the host operating system, the data center, pays for everything. So it sort of resolves this question of why would ACLU or EFF participate in the scheme? Because they don't have technical ability, they don't have resources, and it's not part of their charter to enable these computations. The answer is that as long as you trust that SGXs are guaranteeing that the data center, the host operating system, can't peek inside them, you can rely on the data center for logistics and for the SGX for security. And it suggests that kind of to all of us that a very kind of natural and economical way of running differential private computations is by parties sending their data sealed to an SGX that is going to run, is going to implement differential private computations, from the outside, it's going to look roughly like the original client-server architecture, but without the curator having this unfettered access to raw data. So it's the problem, yeah.
I still don't understand something that feels critical about the setup in your previous slide. When you have these enclaves, on the one hand, you're talking as if it's like a completely insulated space where nothing's coming out, like the lead box.
No,
Nothing's
they can publish. They can publish data. They can
not
release
yet.
data.
It's like, I don't want to, you know. This is my enclave. I don't want to give you access to it. So I'm sort of not getting the threat model exactly. So I could choose to have you access these computations inside my little lead box. Do I have to as part of the bargain?
You can, yes. So basically, the challenger, the application, decides what code it trusts inside the HGX. The code can do something that only the application can see. The code can do something that leaks information or like publishes some information to the outside. The code can, the enclaves can collaborate, can kind of share data between themselves. So it's basically your ally inside the data center. You're like, think of it as like, again, I'm bad with analogies, but like as an embassy. It's like the operating system cannot enter it legally. And the embassy will execute your orders.
So it's someone else making a decision about.
No, you decide what code you're going to run. And the code is, you can examine it, you can authenticate it. It's going to be, if you are not comfortable running this code, you just walk away. So HGXs were not designed to support computations that we'd like them to do. So you have to kind of jump through some hoops. For example, they have limited memory. One of the kind of this canonical problem of shuffling, of taking data and just like re-encrypting it in a random order, you have to do it like given this like we want to operate on gigabytes of data, given this like relatively small window, like secure memory inside the HGX, but it's a technical problem that you can solve. More kind of concerning is the fact that HGXs are not, or the current generation of HGXs kind of has a number of leakage problems, and people who are kind of invested into this fully software view of security, they point out correctly that HGXs are not kind of don't provide this kind of fully isolated environment as they were promised to do. Whether it's a temporary state of affairs or it will stay with us for perpetuity, I have no clue. But that's kind of a concern that like it weighs on the users of HGXs for these purposes. That current generation of HGXs is not as robust as we'd like them to be. Having said that, when I'm talking about HGXs, there's an entire family of similarly of enclaves with overlapping capabilities deployed by other players in the hardware space. Apple has its own secure elements on phones, as made very like prominent by the San Bernardino case. AMD has their own version of HGXs, etc., like RISC-V. So we are looking at the entire kind of space of hardware isolation, and my thesis is that it's going to be super. We have to be aware of it because it actually solves one of the big problems that we have. And another problem that HGXs had was that differential privacy. So their initial implementation was vulnerable to rewind attacks, where you could just reset the HGX and rerun it from the kind of from the same state, and differential privacy doesn't like that, because like you can just exhaust your privacy budget in no time, and there are some solutions to it called monitoring counters that were made part of the HGX model shortly after its release. There are alternative solutions like using coalitions of enclaves to kind of make sure that none of them gets rewind. And finally, we can like think of creative ways of using blockchains. Okay, so I have just a few minutes left, and I want to mention another way of going beyond software. And if these ideas were kind of using HGXs were kind of are fairly mature, like we experimented with them. It's something that is not kind of available in the data center, as far as I can tell. But if there's demand, we'll get there in a few years' time. What I'm going to talk about is like not even half baked. It's like 1% baked, or like negatively baked. You have to dig your out of the hole to get somewhere. So again, this is the picture that we're all familiar with, and kind of a picture that I want you to consider is the one where the database, instead of this neatly arranged set of records, is some set of entangled quantum bits, qubits. And each query corresponds to a measurement of the quantum state. So all computations over quantum states they cannot destroy information, except for measurements that do. And the measurements, they explicitly kind of add noise if the quantum state is set up in the right way. And kind of with each measurement, you kind of will be collapsing this quantum state, and lo and behold, you end up like something that like superficial looks like a exponential wave mechanism. This particular question of whether this quantum mechanics is compatible with differential privacy, it's been asked many times before. This is why I'm saying that like we have to dig out of the negative space, because like I think the answer so far that no one knows how to kind of make it happen, like how to make it work. I want to kind of call out this paper by Scott Ahrens and Guy Robdom, who is like making rounds in the blogosphere, basically it falls into this category of like, or I kind of want to rephrase it as: don't ask what differential privacy can do for you, ask what you can do for differential privacy. So that paper, they use tools from differential privacy to solve problems in quantum computing. And kind of I challenge you to think of ways of using quantum computing to solve problems in differential privacy. So to conclude, I think by accepting hardware as a root of trust, not the root of trust, like in addition to hardware, we have to use some other anchors to bootstrap hardware, not to use it as the only check on, like the only defense. By accepting hardware as a root of trust, we can expand our design space of algorithms that can be implemented in practice and be actually useful. And I also want to expand the definition of hardware, like to also think about some more exotic hardware architectures like quantum computing. Thank you.
Got time for a question while Jintaro sets up? Yeah.
So I guess one question that comes up with any of these architectures, I mentioned, is like the hardware is not the only thing you have to trust here. You still have to like look at the code and inspect it and check that it does what you claim it, what you think it's doing.
Yep.
Right. And it feels like that's a big part of the problem with that sort of distributed software architecture also, right? Like one can imagine models for like funding this distributed architecture, but it's not clear to me what the main obstacle to the existence of these types of like collaborative platforms for analyzing data privately. Is it really like the cost of running the platform, which is what you talked about? Or is it like the fact that we all, in the end, all that software is probably going to be written by one person or one team, and like current state of affairs basically have to trust them to be to operate in good faith and do their job properly.
I think all of it, and what you mentioned. In addition, there's kind of companies are kind of reluctant to rely on someone else as kind of as a failure point, so you just kind of, if you're collecting sensitive data, then introduce someone else into the loop looks kind of wrong.
Okay, but then that raises the point that like, just as not everyone can afford the data that's required for local differential privacy, not everyone can afford the infrastructure that's required to like assemble a platform like the one you're talking about, right?
But just kind of, I want to point to evidence that despite decades of research and a lot of serious efforts in launching commercial offerings in the multi-party in the MPC space, we haven't seen it happening compared to HDXs that seem to be taking off.
Sorry, just more question.
Can I just mention on Adam's last point that I guess you could argue that allowing these rich groups to move from local differential privacy to centralized in a way that's still trusted could be a win, even if we're not yet helping poor companies to implement privacy.
A lot of what we do is about helping Google do it.